All right, let's revisit the concept of differentiability versus continuity, remembering that differentiability implies that the original graph is continuous, but continuity does not imply that if it is differentiable. So let's take this example. F of x is equal to 2 minus x if x is less than or equal to 1, and x squared minus 2x plus 2 if x is greater than 1. Is this differentiable at 1? Sketch the graphs of f and f prime. Well, when I look at these examples, we can state that if we're approaching 1 from the left, then that's going to be 2 minus 1, which is just going to give me 1. If I'm approaching 1 from the right, then that's going to be 1 squared minus 2 times 1 plus 2, which is equal to 1. Which means that this is going to be continuous for f of x. What about f prime? Well, for f prime of x, that's going to be the same as when I differentiate 2 minus x, that's going to give me 0 minus 1, which is going to equal negative 1 when x is less than 1. If I take x squared minus 2x plus 2 and I differentiate it, then I just wind up with 2x minus 2 if x is greater than 1. So I can graph these out. My original one is just 2 minus x when it's less than or equal to 1. So I'm going to wind up with a linear one that looks like this. And then I'm going to wind up with a quadratic one that looks like this. When I graph my differential all the way up to 1, my differential is just negative 1. And then suddenly, at the point of 1, my differential becomes 2x minus 2. Which is going to look like this. Now we can very clearly see that if we tried to do f prime at 1, then that's going to be negative 1 when x is less than 1, and it's going to be 2 times 1 minus 2, or 0, when x is greater than 1, which means that this is not differentiable at x is equal to 1. For example 7, we're already given the graphs. It says, is a graph continuous at this point of A? Well, if I follow it along, I can draw all the way through continuously through A, which means yes. This is continuous at A. Is it differentiable at A? No, we talked about that with the corners in the last lesson, or 2 lessons ago. Is a graph continuous at B? No. Is it differentiable at b? No. So these are easy questions to answer visually from a graph, but what if we're just working from a piecewise function, like the last example? For example 8, if we're going to, for each of the following functions, discuss continuity and differentiability at x is equal to 2, then we're going to say that for this one, limit as x approaches 2 from the left for 4x plus 2 is going to equal 4 times 2 plus 2, which is going to equal 10. The limit as x approaches 2 from the right is going to equal, 4x squared minus 1 is going to equal 2 squared minus 1, which equals 3. And because 10 does not equal 3, this is not continuous at x is equal to 2. Because this is not continuous, it is therefore not differentiable at x is equal to 2. As soon as we know that it is not continuous, it can't be differentiable. For example b, if I have f of x is equal to 4x plus 2 when x is less than 2 and 2x plus 6 when x is greater than or equal to 2, then I'm going to start the same way. I'm going to say that the limit as x approaches 2 from the left for 4x plus 2 is going to equal 4 times 2 plus 2, which is going to equal 10. I'm going to say that the limit as x approaches 2 from the right is going for x squared plus 6 is going to be 2 squared plus 6, which is also equal to 10. So this is going to be continuous at x is equal to 2. What about f prime of x? Well, what do we know about f prime of x? When I take the piecewise, then that's going to become 4 when x is less than 2 and 2x when x is greater than 2. When I plug it in, if I take f prime at 2, then that's going to equal 4 and 2 times 2, which also equals 4, which means that it's also equal to 2 at 2x, where x is greater than or equal to 2, which means that I can state that f prime of 2 from the left is the same as f prime of 2 from the right, which means that it is differentiable at x is equal to 2. And that's it.